Assalamu alaikum. Welcome to my video series on searching algorithms in artificial intelligence. In the previous video, we started informed search algorithms and discussed greedy best first search. In this video, we will discuss A-star search and its variants. A-star actually combines the strategy of two searching algorithms. We discussed greedy search in the last lecture. Greedy search minimizes a heuristic function, the estimated cost from a node to the goal state. It is efficient but neither optimal nor complete. We also discussed uniform cost search in uninformed search algorithms that minimizes the cost g of n from the initial state to the n. Uniform cost search is optimal and complete but not efficient. So one algorithm minimizes the heuristic function while other minimizes the actual cost. So A-static combines the greedy search and uniform cost search to get an efficient algorithm that is complete and optimal. So instead of relying solely on a heuristic value, A-static function combines g of n and h of n. So the new function becomes f of n is equals to g of n plus h of n, while g of n is the exact cost to reach a node n from the initial state, and h of n is an estimation of the remaining cost to reach the goal. Let's understand this with an example. We have same graph and the heuristic table from the previous examples of greedy BFS. We will use a static search algorithm to find a path from A to I node using the updated function h of n plus g of n. Step 1 is to enqueue the start node. We will dequeue the start nodes and we will explore its neighbors that are C, E and B. Now we will calculate the cost for each node. For C, we will apply the function f of n equals to g of n plus h of n. H of n is 329. So g of n is 118. So the total cost would be 447. Similarly, for E, the heuristic cost is 253 and actual cost is 140. So total cost would be 393. For the node B, the heuristic cost is 374 and actual cost from A to B is 75. So the total cost would be 449. Now we will insert these nodes into the frontier in order of priority. So the least cost nodes will come first. So the least cost node here is E with the cost of 393. The second node would be C with the cost of 447 and the last node would be B with the cost of 449. Next we will dequeue the node with the least cost, that is E in our case. We will dequeue E and explore its neighbors G and F. Now we will calculate the total cost for G and F nodes. The heuristic cost of G is 193 and the actual cost h of n from A to G is 140 plus 80. This is similar to what we did in uniform cost search. Similarly, for F, the heuristic cost is 178 and the total cost from A to F is 140 plus 99. Now we will insert them into the priority queue. Nodes G and F will come first as they have a smaller cost than C and B. So now the node with the least cost in the queue is G. So we'll dequeue it and explore its children. It has only one child, H. Let's calculate the total cost for the H node. The heuristic cost from H to the goal is 98 and the total cost to reach from A to H is 140 plus 80 plus 97. It will be inserted at the first position in the priority queue as it has the least cost. So the next node with the least cost is H. So we will dequeue H and explore its neighbors, that is I. The heuristic cost for I is 0 as it is a goal node. And the total cost to reach from A to I is 140 plus 80 plus 97 plus 101. So the total cost for I would be 418 and it will be inserted between F and the C node. The next node in the queue is F. So we'll explore F and explore its neighbor. The neighbor is I. So we'll calculate the total cost for the I node. The heuristic cost is 0 and the total cost to reach from A to I via F is 140 plus 99 plus 211 equals to 450. Now we already have I node in our queue. The cost of this node is greater than the cost of the node that is already in the queue, that is 418. So we will not insert it again. So the next node in the queue is I node. We will explore it and test if it is a goal node or not. Yes, it is a goal node. So no further expansion will take place. So the path used by the A-static algorithm to reach the goal is A, E, G, H, I, and the total cost is 418. Let's update the heuristic value of the H node from 98 to 138 and check if it is optimal. After exploring the root node, we will get C, E, and B. So the total cost by adding the heuristic value and the actual cost in front of each node. C has the total cost 447, E has 393, and B has 449. So the algorithm will move to the E node. After reaching E, it has two options, G and F. So the least cost node is G, so it will move to G from here. The neighbor of G is H, but it has cost that is greater than all other explored nodes. So the node with current least cost is F with a cost of 417. So the algorithm will move to node F. The neighbor of F is I. It has a cost of 450. We have another node C that has lesser cost than this node. So it will move to C. D has a cost 473 that is highest among all. So the least cost among currently explored nodes is B with cost of 449. So it will move to the B node. Now the next node with the least cost is I, so it will move to I, and I is the goal node. Now the path would be A, E, F, I, and the path cost would be 450, which is not optimal. Let's understand why this happened. Actually, the heuristic function used in the previous example was not admissible. A heuristic function is admissible if it never overestimates the actual cost from node n to the goal. This means the heuristic cost should be less than or equal to the actual cost for all nodes, ensuring that A-static never chooses a non-optimal path. If h of n always underestimates the actual cost, A-static is guaranteed to find the optimal solution. Let's further understand this with an example. In our original heuristic table, the heuristic value of the H node was 98. The admissibility condition is that the heuristic cost should be less than or equal to the actual cost. So the heuristic cost is 98 and the actual cost to reach from H to I is 101. So 98 is less than equal to 101. So the heuristic function is admissible. Now let's see the other case where we modified the heuristic value of H node from 98 to 138. Now the heuristic value is 138 and the actual cost from H to I is 101. Now 138 is not less than or equal to 101. Hence the heuristic function is not admissible. Let's discuss the properties of A-star search. A-star search is complete. It will always find a solution if one exists, as long as the branching factor is finite. A-static is optimal if the heuristic is admissible and consistent. The worst case time and space complexity is exponential, but in practical cases, A-star finds the solution more efficiently and quickly than the uninformed search algorithms. A major drawback of A-star search is its high memory usage, as it stores all nodes in the memory. To overcome this, iterative deepening version of A-static uses a depth-first search approach with a gradually increasing cost threshold, reducing the memory requirements while maintaining the optimality. It explores nodes within the current cost limit and increases the threshold iteratively, making it more efficient for large search space despite some redundant node expansions. While it may re-expand nodes, it reduces memory usage compared to A-star search. If you found this video helpful, don't forget to like, share and subscribe for more videos on data science and AI. See you next time.